Good afternoon, everybody. Thank you all very much for joining the last day of our session. On behalf of the conference organizing committee, that is Carrie, Jessica, Joe, Ansel, and Massey, I welcome you to the final day of the 4-day Location Intelligence Knowledge Exchange, Mother Earth Edition. I'm Arthur Beryl, Distinguished Technologist at RBC. Just a couple of notes. We have a real treat for you this afternoon, by the way, with a collection of very interesting papers. I think you'll enjoy that, and two great speakers to conclude the session. But before we start, just a couple of things. Have a look on the top right-hand corner of the conference tool, and you'll see a Q&A section there. So please avail yourself of that. If you see something coming along you want to discuss or you want to put questions, please put them in there. And Asan, the convener of the paper section, will pick the questions out and translate them for the speakers. There's also a down arrow in that same place. If you hit that, it will move the sidebar and give you a bit more real estate in your screen. Also, there are virtual booths, so please do visit those booths. There's several sponsors are there, and they're ready to speak to you about what they've got. There are tables available, virtual tables. You can pick up a virtual table, give it a theme, and collect there for conversations and discussions. Our sponsors, the conference could not have proceeded without contributions from our platinum sponsor, Microsoft, gold sponsors, Cato and RBC. Thank you all for being sponsors. It's made this conference a big success. And with that, I'm going to hand this over to Asan, who's going to orchestrate the paper sections. Over to you, Asan.
Amazing. Thank you, Arthur, for the great introduction. Let me start by saying that it's a
We seem to have lost Asan there. He's gone.
Oh, really? What?
Yeah.
When did you hear? Did you hear the intro?
No, we lost you. You went on mute. Something
Oh, interesting. Yeah, I don't know what happened. Okay, so I'll just say that again. Well, I'm the academic chair of the conference. I welcome you dearly and warmly to the conference. We have a brilliant set of papers, queued for you. The first one is a study on the effect of daily weather on quarterly retail revenues. This work is done by University of Toronto and RBC, and it's presented by Susan from University of Toronto. Please take it away, Susan.
All right, thank you so much. I'm just gonna share my slide here. Can everyone see the slides? I think they're up now. So hi, everyone. My name is Susan. I'm a student at the University of Toronto studying engineering science, and this research work was conducted through the University of Toronto's Center for Management Technology and Entrepreneurship in collaboration with RBC. Okay, so quick introduction is that the physical risk of climate change is expected to cause the global economy to lose 10% of its value by 2050. And this was from a recent study conducted by the Swiss Re Institute. And existing research has shown that weather events that depart from seasonal cycles have a significant effect on the monthly retail sales of companies due to changes in consumer behavior, as well as investor perception. And so the motivation behind this research was to try and replicate this understanding of how weather impacts retail companies, but instead on a quarterly level. And hopefully this information will help institutions improve their pricing and mitigation of these physical climate risks. So the objective of this research was to develop a model which is able to quantify whether a company's quarterly financial revenues are impacted by outlier weather conditions. And so the challenge here really was that existing literature really focused on the impact of weather for daily sales transactions. However, that data is often proprietary, and so we wanted to explore how weather events ultimately impact a company's quarterly financial revenues, which is all publicly available information. And so the scope was Canadian companies that are located and operating in North America in the consumer staples and retail sectors with, again, publicly available financial data. So here are two kind of key literature that a lot of this work was based on. Both these papers are from Europe, and these two papers were very similar in terms of methodology, but their findings and also the scope at which they operate in were quite different. So for the first paper was the impact of daily weather on retail sales, an empirical study in brick and mortar stores. And this was a German retailer that used daily sales data for 673 stores in Germany. And the parameters that they used were temperature, precipitation, and sunlight. And they developed this random coefficient model that was able to find that daily sales in the stores were impacted up to 23% based on the store location, and then up to 40% based on the sales theme. So we can see that there's a difference not only in where the stores are located, but also sales theme. And so for our study, I'll get into this a bit more later, for our study, although we're not able to segment out the specific sales themes within our retailers, we try to analyze and study retailers from different sectors to kind of mimic the comparison of sales themes. And then the second paper, it's the weather, quantifying the impact of weather on retail sales. So this is a UK retailer using daily sales data from 2,000 stores. So 2,000 stores is a bit more on the scale of the lot of retailers that we're studying in Canada, especially because the weather in Germany is fairly homogeneous versus in Canada we have quite different climate from the East Coast to West Coast. So what this model did was a random forest model using very similar weather parameters, again, temperature, precipitation, wind speed, and humidity. And what they found that the effect was most noticeable in summer and spring, and that wind was the most influential weather parameter. So our methodology is, a lot of it is based off of the two previous papers. However, we are, instead of working on a daily scale, we're working at a quarterly level. So the methodology is segmented into three key components. That is the data aggregation, the feature engineering, and then the model construction itself. So for the data aggregation, it was really important that we build a pipeline so that we could easily acquire the data of several retailers. And the first piece is the quarterly revenues. So three pieces of data. We have the quarterly revenues, the retail locations, and then the weather parameters themselves. So for the quarterly revenues, we obtained most of these through CDAR and also the Yahoo Finance API. And so for most retailers, we were able to obtain 10 plus years of quarterly data. But that's still quite of a challenge when you consider the fact that that's still only about 40 data points. And for a retailer with maybe 20 years, we have 80 target data points. But for the retail locations, we use the Google Maps API. So this API is publicly available, and we're able to obtain all the locations of the retailers. So for each retailer, we studied 6 retailers, and they all had about between 500 to 2,000 locations. Finally, the weather parameters, we took it from Ordinal, Daymet, and this data is gridded data up to 1 kilometer. So for every single location, store location, we're able to pull the historical data for the past 10 years as well. In terms of how we transform these features, the main thing was we had to select the weather parameters that were most appropriate for our climate. And those happen to be temperature, precipitation, snow, water equivalent, and then short wave radiation, which is equivalent to sunlight. And then next, similar to some of the previous papers, we wanted to isolate the outlier weather. So we took a numerical approach, so taking the historical distribution for every single store location, we compare how each of these weather parameters rank in terms of the historical, and then we take the tail 5% and the head 5%, and we consider those to be abnormal. And then finally, we aggregate these features across all the locations and quarters. So this is where we were most concerned that a lot of the signals would be lost and washed out at a higher, more abstract levels. But we aggregate it across every location for each day, and then we aggregate that per retailer in a quarter. So then the final model construction is a multiple linear regression approach. And you can see the formula there, but we do take the ln of the quarterly revenues, which is pretty consistent with the previous papers. So here is a sample of some of the data that we had obtained. So for Loblaws, you can see here mapped all over 1,000 locations in Canada. And then also for the revenue, this is the revenue. So we do some data cleaning to mitigate. You can see for Loblaws in 2014, it made a major acquisition, which is what caused a major spike in its revenue. So we do some data cleaning to remove these steps, cyclical and seasonal trends. And then also at the bottom, you can see the weather parameters. So for our 6 weather parameters, we ended up using 4 of them in total. So final results and conclusion. What we found was that grocery, so the 6 retailers that we studied were Metro, Loblaws, Empire, Canadian Tire, Leon's, and Indigo. So we have stores that are from the grocery, the furniture, consumer staples, retail, etc. And what we found was that most of all 3 of the grocery retailers had fairly low R2 values. I don't have the feature kind of coefficients pulled up for all of the retailers here, but I've pulled Metro as a sample, and you can see that the coefficients are quite low when you compare to something like Canadian Tire. And what this suggests is that for retailers that are in the consumer staples or grocery sectors, the purchasing behavior is relatively invariable throughout the year, and despite abnormal weather. Similarly, we can, furniture purchases are generally larger purchases that require preemptive planning on behalf of consumers. So we don't see as much seasonal variation or sensitivity to certain weather parameters. But on the other hand, for the hardware and home retail sectors, we see much more variation in terms of magnitude and directionality.
So you got 1 minute left for the presentation. Susan, sorry for the interruption.
No worries. That is the end of the presentation. Some kind of next steps that we are currently exploring, because the work on this is not done yet. This was just kind of an interim a short paper. We are going to explore unsupervised learning models that can potentially improve the anomalous weather detection and expand to more retailers. Hopefully we can expand up to tens and dozens of retailers to have a better sense of retail sector variation. Thank you so much.
Okay. All right. Brilliant presentation. Well done, Susan. So We got a couple of questions for you. I tagged them to the stage. So the first one is, how did you decide which weather parameters would be the ones studied?
Yeah, so in order to decide the weather parameters, we looked at kind of correlation between them. We didn't want any weathers that were too highly correlated. So, for example, vapor pressure was one of the ones that we were looking at, but it was too correlated to temperature. Vapor pressure is like humidity. So we kind of rejected a lot of parameters. And then there were also some parameters that we were limited just because we didn't have we didn't have that gridded, we didn't have sufficient data. So like wind was one that we wanted to incorporate, but we didn't have access to that data.
Okay, beautiful. So I'm tagging the second question. They're asking, why did you see, why is indigo showing such a variation? Is there any
Yeah,
indication as to why?
well, I think Indigo also experienced the most growth out of all the retailers. It's the most newest of all the. We do detrend for that. We think that it's because it's such like a more new retailer compared to the other ones, and it's most sensitive to seasonal consumer behavior patterns, which is why it could have been most susceptible. It's more of like a leisure goods versus the staples.
All right, beautiful. And there is another question, this one from Richard. I surely put it on the screen. In quarterly earning calls, CEOs and CFOs will explain deviations in revenue from expectation, such as blaming supply chain or hurricanes. Did you consider using earning call explanations as a potential method for validation?
No, we haven't, but that's actually a quite a good idea to try and validate that for specific quarters where we observe a greater change in that. So yeah, that's definitely a great suggestion.
Great, good piece of data. Okay.
Mhm.
All right. So without further ado, let's end this session. Thank you very much, Susan. Moving on to the next speaker. Let's join me in thanking Susan. Okay, so next up is self-supervised learning for time series from multispectral satellite imagery by Richard Brath, and I'm super excited for this one as well. Self-supervised learning is a very active area of research right now in deep learning. Richard, please take it away.
Thank you. And can you also add Chris Bethune?
Hi, Richard. I think I'm on.
Okay, great. So you should be seeing my screen now.
Yeah, if possible, let's pin Chris too. All right. Yes, we can see the screen now.
All right, great. So thank you. I'm Richard Brath, and we're presenting about machine learning on satellite imagery to create time series. And let's see this advance, please. There we go. So before we jump into the satellite imagery, we need to start at the larger project. It's a project called Distill. The goal of Distill is easy to use machine learning by people who know their field, but they're not data scientists. And it works with many kinds of data like tabular data, time series data, and imagery. You can think of it as a pipeline where we collect data on the left side here, and it goes through a number of steps, and we end up with predictions on the right side. We'll start with a really simple example of classifying fast food. So what we have here is the data loaded on the first step. The screen is split into two parts. The left half is a summary of the data variables. And in this case, we have two variables. We've got the images and we have labels, whether they are hot dogs or not. And then on the right side, we have instances of the data so we can see a number of the images. The user picks one variable to be the target. That would be the label that we want the system to predict. And then we pick what we're going to use for the training for the model. In this case, we're using the images. And then we're going to press a button. The models run. It takes a little bit of time. And we get results back, which you can see on the right side, which show us things like scores and error, for instance. We can see incorrect results, such as not properly classifying tacos. And then that was the detailed data expression there. Okay, so we move on from fast food to satellite imagery, and there's a few more challenges. The data is massive, There's multispectral imagery. It's more than just red, green, blue. There's 9 other wavelengths. There's noise to deal with. The data isn't neatly labeled, and so on. And the core of our approach is a convolutional neural network as the backbone for all of this. We have the user interactively train this network, and then we can use the neural net for tasks such as classification, segmentation, and image retrieval. So our first example here with the satellite imagery is together with information from field offices about the presence of insect infestations. In our incoming data, we have the satellite imagery as well as geographic coordinates, so latitude, longitude, we can put on a little map. We have timestamps on here. And we also have the extra data, which is whether there was infestation or not reported in the area. This table is just showing a list of all the data. We can inspect the images in more detail, look at different channels, zoom in, and so forth. And we can then look at images where only things are true or negative and so forth. And then we're going to set up the model the same way that we saw before. We're going to choose a target. We want to use the labels. And then in this case, we'll use the images and the geo coordinates and build a model based on that. The model has a few parameters. We run that and we get the results back. In the results, we can see our metrics. We can also plot that, for example, on the map. And by plotting it on the map, that allows us to use our local knowledge, for example, areas that might be more prone to infestation. So not just the machine learning model, we can use this kind of macro scale understanding of what's going on. We've also got micro abilities to detail into the individual images and see what the network is attending to and so forth. And then once we have that model, we can apply it to other data sets. We can look at different areas, or we can look at newer data, for example, and then zoom in and see where are the areas of high probability of infestation. So now we're going to take that model and we're going to look at how we create the model when there's no labels. How do we handle that? So we've got the same data set. Now we want to identify agricultural areas, and we have a variable but no labels associated with it. Our first step is to navigate and zoom in the map and go to some known agricultural locations and then click on the positive button. We do this a couple of times, then we can search for similar images. And we can then get back results of the images, and they're color coded so we can see where there's areas, even just at this very rough level, where there are areas that are positive or negative. We can zoom in, we can click and drag many examples and label them and do search similar again. So there's an iterative approach here to label the data. And after we do that a couple of times, we've got a couple hundred images labeled, and we can go back to the steps to create the model, inspect the output, and apply it to the latest data and see our results. And we might want to repeat that a couple of times to handle some additional situations. For instance, clouds were a problem in this particular run of the model. Now that we've got two different models, we can combine those outputs together, and we can say, for example, we've got the color coding for the insect infestations. We've got the agricultural land, so we can filter that out, and we're getting down to areas that are most vulnerable, for example. And we can join other data as well, so we can put in irrigation or demographics and so forth, and get down even narrower to the exact areas that you might want to focus on to deal with your potential infestations. Okay, so there's more to it than that. Until now, the entire image has been treated as agriculture or not. The same labeling data that we created can be used to extract sub-images. Once you've got thousands of images distinguished as agriculture or not, the visual cues that the neural net used for identification of agriculture can be used to segment the data into the parts of the image that are agriculture or not agriculture. So this is more efficient than attempting to label every little section of the image, and our results are pretty promising, as shown in the image column to the right here. Doesn't exactly match the ground truth, but we're getting some reasonable results here. And then we want to expand it to time. We're trying to get to time series. The time series are useful because then we can predict within the time dimension as well as the spatial dimension. For example, are conditions trending worse or better? This creates new challenges such as gaps in the time series where the data is missing. So we still have to experiment with how we might be able to fill those in. So this is a discussion on a work in progress. The results are promising. There's low effort for non-experts to create the labels, build models, apply them. It's working on multispectral satellite imagery and using all of those channels. And we are in a transition from research to actual deployment for agricultural uses. Future work does mean we need to do more on the time series work, being able to aggregate across scales and also look at potential machine learning techniques for interpolation across time series gaps. So thank you.
Okay, brilliant. Thank you very much, Richard, for the great presentation. There are a couple of questions. So let's ask the one from Arthur first, showing on stage. Could you use the gap filling to do regional interpolation to handle cloud cover, find the clouds and gap fill?
So Chris, I don't know if you're on.
Yeah, I've got that one. Yeah, so I'm trying to unpack that. So there is quite a bit of research that's done, on gap filling. We have some facilities where we'll backtrack the data as we're looking at current timestamp. We'll actually at an image level try and find an unobscured image and put that in, and we'll go back, a certain limited time period to do that. I think there is work that's been done where they're trying to do it at the pixel level so that you could actually identify a region of cloud and then swap that in. So we haven't tried to do any of that. We were just working at individual tile levels initially.
Okay, this is brilliant. So we have another one from Charles. Have you looked at hyperspectra such as Everest and multispectral data?
So we looked at Sentinel for multispectra being 12 band. We also took a look at Landsat, which I think is 7 or 8, but we haven't looked at anything hyperspectral yet.
Okay. I also have a question. So the method that you named the method as self-supervised, and then the one that I heard was kind of labels being generated. Is it a data augmentation method, or is it actually self-supervision taking place? So in self-supervision, the data learn, the model learns from the data or the sequence or the structure of the data itself, and the kind of the label, the task is designed such that it can be learned directly without labels being manually relatively generated. So how do
This
you?
is still a human in the loop system. So we have the user creating labels.
Right. So where the self-supervision comes in is we actually, because there is no large corpus of satellite imagery that's labeled like an ImageNet, what we used was self-supervision to actually build up our embedding model from the Sentinel-2 data. So we downloaded massive amounts of Sentinel-2 imagery, used, I think the technique was called AMDIM. We also experimented with MoCo, momentum contrast, and then we built up the embedding models from there. And then that acted as the backbone for a series of other tasks we did. So the labeling task, what we're doing there is using the embeddings and cosine similarity to find similar images to help the user quickly label a large set of tiles so that then they can, move on to actually fitting, in our case, just lightweight classifiers like random forests and SVMs.
Amazing. So the labels were available mostly for the downstream tasks. The original kind of embeddings were trained with self-supervision.
Yes.
Okay, brilliant. We had 2 more questions. Let me see if we have time. Okay. Yes, barely. So we have a little bit short of a minute. 2 questions. Is the SW available to test?
So we have it. It's up on GitHub as a repository right now. It's very much sort of work in progress experimental software. So it's there and can be explored.
Okay.
like anything, not ready to be thrown over the fence necessarily.
Beautiful. So if you're comfortable, please share the link with the audience in the chat. Otherwise, I suspect the link will be available in the paper as the papers get published. One last question: is the project this still open sourced?
Yes.
Okay, brilliant. All right. Well, I'd like to thank you, Richard, Chris, and team for the brilliant presentation. I really look forward to this work and the next versions of it. Look forward to read the entire paper as well in the proceedings. Thank you very much.
Thank you.
Okay, brilliant. Thanks very much. So next, we have automated traffic incident detection with two-stream neural networks. This work comes from Vector. And the presenters are Andrew and Matthew. Over to you.
Sounds good. You guys can hear me okay? I'm going to share my screen.
Yes.
Yes, we can.
You guys see the slide okay?
Yes.
Okay, sounds good. So take it away, Andrew.
Okay, so thanks everybody. First, some introductions. So my name is Andrew Alberts. I'm a data scientist at Intact Insurance. I work mostly on using telematics data and alternative data sources to price auto insurance.
And I'm Matthew Cowell. I'm currently doing my PhD at York University, and I'm also affiliated with the Vector Institute and a scientist in resident at Next AI.
Great. So today we'll be talking about some work that we did take on at the Vector Institute, automated traffic incident detection with two-stream neural networks. So first, I'm going to start off with sort of why we took on this project. So I'm sure a lot of you know that dash cams have become a lot more prevalent, especially in North America over the past few years. So when you drive in an Uber or a taxi, you probably see that they have a dash cam, pointing out their front windshield. And dash cams are great as they act as faithful witnesses to events surrounding the car when it's on the road. And footage from driving cameras are frequently used in my industry, so they give a lot of evidence to help settle auto insurance claims, and that's really great. And we'd like to make use of large quantities of these types of videos, but obviously to make this work at scale, it's necessary to be able to automatically detect specific hazardous events that are within these videos. And so from that, techniques from computer vision and neural deep learning provide a solution to this. So just our problem setting. So again, our goal was to try to identify traffic accidents from dash cam footage. And we needed a data set to train our model on. So we used the detection of traffic anomaly data set called DOTA. And this is openly available on GitHub. So just to give you guys a bit of a taste of the video data that we had, here's a couple sample frames. So first off, there's anomaly labels. So these are frame level labels indicating what type of event or incident took place in the video. So in this example, there was a collision with another vehicle moving ahead or waiting. So that's a frame level label. And in these incidents, the sort of subjects of the accident are also labeled. So there's a bounding box which localizes the various subjects. So whether it's a car or a pedestrian, and there's also a label for what that subject is. So in this case, we have a car. Now for our methodology. So we wanted something efficient, modular, and flexible. So we wanted efficiency, obviously, to be able to rapidly train and test our model. We wanted something modular since this was an industry academic partnership project. So we wanted to be able to experiment with many different things. And we wanted flexible output in our model. So as you saw, we want to be able to do both detection of the objects and classification of what the objects are and what the incident is.
And so to fit with these constraints, the model we ended up choosing is the You Only Watch Once, or YOWO, convolutional neural network architecture. So now let's go through the architecture in detail. So the architecture is a two-stream architecture, which consists of a motion stream, which is a three-dimensional convolutional neural network, which takes as input a 16-frame video. On the other side, the other stream, we have a spatial stream, or a 2D convolutional neural network, which takes as input the final frame of the video, which is the frame that the prediction will be made on. So the output of these two neural networks then get passed to what's called the channel fusion and attention module. And really the purpose of this module is to relate the spatial stream features over time and say, for the frame of interest, what features over time relate and give us information about our final frame of interest. So this representation gets passed through a final convolutional layer and two predictions are made. The first prediction is the detection of objects which are in the collision. So we have the class of the object and the location of a bounding box. The second prediction that's made is anomaly classification. So it's actually, as Andrew mentioned before, per frame, what accident is occurring in the video itself. So we train the model with two different loss functions. One is the bounding box loss on the class and the location of the bounding box of the objects. The second is simply a classification loss for the anomaly. Our final loss function is here at the bottom, and you can see we've added a weighting parameter, lambda, on our proposed anomaly classification output. So here's an overview of the experiments that we ran. On one hand, we had architectural modifications. So mainly we focused on the different streams and how they relate to performance. On the other hand, we have loss function modifications. So we added this anomaly loss and we wanted to see what type of weighting worked best for our model. So in terms of choosing the 2D and 3D backbone for the motion and appearance stream, we tried all of these models here and we've ranked them in the most amount of parameters and to the fewest number of parameters. Now, interestingly, the best combination was both models having the fewest number of parameters. Now, we believe that this is because the model is probably overfitting to the data, and maybe there's too many parameters relative to the number of data samples, which we confirm in later experiments, as you'll see. So now that we have the backbone selected, now we're going to evaluate the loss function, and we want to answer the question, what lambda value is best to train the model? So you can see here the loss curve, or the accuracy over training, and a weighting of 5 and 10 actually learns significantly more than other weightings. So it's kind of difficult to see which one's better, but looking at the per class accuracy here on the right, you can see that for most classes, the lambda weighting of 5 works best. So this is how we tuned our loss function. Finally, we'll show some qualitative and quantitative results. So we achieve a final F-score, as you can see at the bottom, which is the average of the precision and recall of detecting the objects of 53.6, and a final anomaly classification accuracy of 48.3. On the left, you can see the per class accuracy, and interestingly, class ID 1 and 7 get a performance of 0 F-score. So if we look at the number of examples, there's actually only a few dozen videos for class 1 and 7, while for the other classes, there's upwards of 500 to 1,000. So some classes are much more rare and difficult for our model. We can take a look at some qualitative outputs, and you can see our model actually detects the objects and anomaly or accident of interest in a variety of weather situations. However, with more rare accidents, such as the pedestrian in the top left, or cars that are or accidents that happen quite far away, our model has a pretty difficult time detecting these properly.
Great. Now to end off, I just want to talk about some industry applications to this type of system. So on the left, I talk about insurance risk measurement, pricing, and selection. So obviously, dashcam video can really give us new, fresh indications of drivers that are taking on risky behaviors and what those behaviors are. And this sort of new type of information can really add a lot of value to pricing models. On the other side, I talk about driver training. So this would be more of interest to somebody like a fleet manager who wants to see how his or her drivers are driving, and then see if they're sort of engaging in any risky behavior, and then from that give tailored guidance to that driver to correct his or her driving patterns. And just now to end off, some conclusions in future work. And I think it's obvious from the presentation that the model works well for classes with a lot of examples, but not so much for rare classes. and that we had difficulty detecting anomalies at far distances. So in terms of future work, we'd like to better understand and correct the impact of overfitting, improve the performance on unbalanced classes, and finally, to really make this type of system more useful, we'd want to be able to actually discriminate between anomalous and non-anomalous driving so that we could really pinpoint where the issues are or where the risky behaviors are. And that's that. Thank you.
All right, brilliant. Thanks for the great presentation. So a couple of questions. One, let's actually ask just one question and then move on to the next presentation because we're a little bit behind on time. But so you have there was an anomaly detection cost function, and there was a object detection. So the object detections are kind of with labels, and you actually localize as well. So there are bounding boxes as well. So that's I imagine is labeled from the data set that you're using. But how did you? So the anomaly detection that was unlabeled and unsupervised to some extent, or how could you tell me a little bit more about that?
So the anomaly classes were labeled for each video. So this is a pretty interesting data set because it has both the local detection, the objects and their bounding boxes, but also another separate set of labels per video, what accident occurs. So we do have the labels. It's fully supervised.
Amazing. And what do you think of the scores? Like the fact that do they compare with other benchmarks? Perhaps it wasn't the purpose of the study, given it was a short paper, but how do you interpret the scores?
So I would say that the other benchmarks on this data set usually also incorporate a anomaly detection component. So we didn't consider that. We just tried to detect the accidents and classify them. While in the other papers, they actually get maybe a 10-minute long video, and they try and also classify which frame does the anomaly start and end. So it's I'd say ours is reasonable if you only considered the object detection, but they also had a harder task, which is considering the temporal scale of it as well.
Gotcha. This is brilliant. Thank you very much, both Matthew, Chris, and team. I see that Chris has also shared the GitHub of the repository regarding the previous talk. Thanks very much, and I hope to read the the paper when it's published in the proceedings. Thanks very much.
Thank you.
Okay, brilliant. So next we have a comparative study of semantic segmentation models for building footprint extraction using satellite imagery, also from Vector. Go ahead, John and Jinbiao.
Yeah, thanks for providing the opportunity to present our study. My name is Jim Ling. I'm from Thales Group. And John, can you introduce yourself? Oh, you're mute.
Hi, my name is John. I'm at Vector Institute as well as Western University. Super happy to be talking with you all today.
Okay, thanks. And I will present half of this presentation, and then John will present the final part of this presentation. The topic of this presentation is a comparative study of semantic segmentation models for building footprint extraction using satellite imagery. This presentation divides into 5 parts. First, we will introduce the problem setting and motivation, followed by the experiment dataset, methodology, results, and at the end, we will present the future work and conclusion. Yeah. The goal of this study is to extract the building footprints from the satellite imagery, as we can see in the left figure, and then we extract the buildings in the right figure. It has the background and the buildings. And in traditionally, this building is extracted manually, which is time consuming and costly. So the motivation is we would like to apply advanced algorithms to extract building automatically, which serves important downstream use of metadata, including humanitarian and disaster response. Before we go into the the dataset and algorithms, I'm going to briefly introduce the semantic segmentation. The semantic segmentation is to segment new samples in the image into the classes defined in the training set. For example, in this figure, there are 3 classes: person, bicycle, and background. The objective of semantic segmentation is to segment this image into these 3 different classes. So the data set we explore is the SpaceNet 2 with more than 10,000 high-resolution satellite image from 4 different cities. There are 2 classes, the background and building. We divide them into 80% training set and 10% for testing, 10% for validating. The recent advanced computer visions and these semantic segmentations provides a great opportunities for us to precisely extract the building footprints. And we apply several popular and advanced semantic segmentation methods to this study. And here there are 4 different architectures: the UNet, UNet++, FCN, DLab v3. These are very popular and advanced architecture. And I'm going to introduce the UNet and UNet++. At the left side, it is the UNet. The UNet is an encoder and decoder architecture with the SCID connection from the encoder to the decoder. And it has a U shape, so that's why it's called UNet. And UNet++ is improved from the UNet. It not only has the SCID connection, but also the convolution layers between the encoder and decoder. So, and then I will pass this to John. He will present the final part of this presentation. John.
Awesome, thank you. So the third approach we explored is fully convolutional networks, or FCN, which is a pretty seminal work in the deep learning for semantic segmentation literature. It consists of a backbone that maps an input image to a set of convolutional features that are then upsampled to the size of the predicted semantic map. So we explored 2 variations of this architecture, one with a ResNet 50 backbone and one with a ResNet 101 backbone. These are both pre-trained backbones, which is in contrast to UNet and UNet++, which do not leverage any pre-training. Moving on to the next approach, we explored DeepLab v3. And DeepLab v3 is a method for semantic segmentation that has been recently proposed. Jim Bao, can you just move to the next slide, please? Perfect. Yeah, so DeepLab, it consists of an architecture. One of the defining features of the architecture is the use of dilated convolutions, which prevent excessive downsampling of the feature maps and thus improve semantic segmentation prediction. We also explored ResNet 50 and ResNet 101 backbone for this model that were pre-trained. So these are the results from our experiments. We evaluated the aforementioned models on the SpaceNet dataset by first training each one of them on the same train set and using a validation set to define a stopping criteria for the training procedure. And then finally, we use a test set to get an estimate of the out-of-sample performance of each of the models. So not surprisingly, DeepLab v3 with the ResNet 101 backbone got the highest score. We measured performance in terms of intersection over union, which is commonly used in semantic segmentation. And it's essentially a measure of overlap between ground truth object instances and object instances predicted by our networks. So DeepLab got the best performance, but it was followed closely by DeepLab v3 with the ResNet 50 backbone and the 2 fully convolutional network variations we explored. Down at the bottom is UNet and UNet++. They still obtain better than chance performance, but it's a lot less strong compared to the other methods. And this kind of stems from the fact that I mentioned we're exploiting pre-trained backbones for both FCN and DeepLab. So this is definitely going to give them a bit of boost in performance. And that's one of the reasons we think the top 4 methods perform better on a relative basis. Moving on to the next slide, we can take a look at some of the predicted semantic maps for 3 images in the test set. So on the far left, you can see 3 different images. Some are densely populated with building footprints, some are not. And pretty much across the board, we're able to get pretty robust performance. But we can definitely see in the case of UNet and UNet++, there's a bit more false positives. And the DeepLab and fully convolutional network variants tend to perform a lot better. Moving on to the next slide, we can see the train loss and the validation loss, which is cross entropy in this case. And we can plot it across epochs. So we can see that the models that leverage pre-training, not surprisingly, converge a lot faster since they benefit from seeing other data before training. This is another thing to notice here is that they tend to start to overfit a bit faster. So in our experiments, we use like an early stopping criterion. It's definitely important to include that. So now we'll talk about a few applications that are downstream from semantic segmentation in satellite imagery. So one cool one that I've kind of encountered in the literature is disaster impact assessment. So on the left-hand side of the slide, you can see we have 2 images. One is taken prior to a natural disaster, and one is post a natural disaster. And we can see there's a pretty big difference between the 2 images. So one application of semantic segmentation for building extraction in satellite imagery is to basically do a disaster impact assessment. We can take a look at the pre-image and compute the predicted semantic maps, which are going to kind of show where the buildings are. And then we can do the same thing for the image that's from following the natural disaster. And by taking the difference between the 2 predicted semantic maps, we can see generate a heat map that kind of approximate where the most damage has been done by the natural disaster. And with that information, maybe we can plan a bit better about how to allocate resources. Moving on to the next application, this is a project that I've kind of worked on a bit, so I wanted to include it, but parking lot occupancy assessment using satellite imagery. So we know retailers have parking lots, and a lot of them are kind of concerned about the allocation of the parking lots. So one application of kind of semantic segmentation or object detection methods in satellite imagery is to be able to generate basically parking lot heat maps that will map the activity of different parking stalls in the parking lot. So you can generate a heat map and maybe use this to kind of allocate space more efficiently. Moving on to the next slide, these are just some points for future work that we want to explore in the future. So
John, just letting you know, time's up. If we can just say them in the next few seconds, would be amazing.
Yeah. So sorry about that. So we can explore different approaches in different data sets. And that would be the primary future work. And then just in conclusion, DeepLab v3 with the ResNet 101 backbone was the strongest performing model, and transfer learning is definitely beneficial in this setting. Just like to thank all the team, which includes Jim Bao, Tristan, Rex, and all the people at Vector and the associated sponsors that were a part of the project. And thanks everyone for listening.
Brilliant. Great work. Thank you very much. I'm going to skip the Q&A I have personally a few questions, but we have to skip it. Thank you both Jinbiao and others from Vector who presented. Thanks so much. So let's move on to the next presentation. Okay. Okay, next one is 5, object detection for autonomous lawnmower based on YOLO version 3. This is Gabrielle joining us from Florida Polytechnic in Lakeland, Florida. Go ahead, Gabrielle.
Sorry, yes. Let me just share my screen. Oh, share screen. Would like to share this one. Okay, I hope that okay, great. You guys are seeing my screen. Okay, can everyone hear me perfectly?
Yes.
Awesome. So hi, and everyone is seeing the PowerPoint correctly as well. Okay, great. So I did object detection for an autonomous lawnmower based on the YOLO version 3. So hi, my name is Gabrielle Sims. I'm a master's in computer engineering here at Florida Poly. A little bit more about me beyond that is that I work in the Advanced Mobility Institute here at Florida Poly, where I get to work with other professors and other students to build autonomous systems. And so this project was a great opportunity to use computer vision inside of my work. So the objective of this program was to okay, I see that you guys can't see my screen. Give me a second, I'm sorry. Yes. Okay. Are you guys able to see my PowerPoint? I'm so sorry.
Yep, now we can see it. You can full screen for
great.
presentation mode, please. Thank you.
Okay, good. And then it's doing this thing. Okay, great. So, sorry, we're past this part. Yes, so the objective of this project was to create an object detection algorithm for an autonomous lawnmower that will work primarily inside of an airport environment. So to start, we wanted a simple solution that would simply just recognize if there was an object in front of the mower, and later it will be trained to recognize objects that was typically found inside of an airport environment. So one of the main constraints of the project was that the project should remain low cost. And so while we wanted the program to also be able to estimate the distance, we tried to exclude stereo cameras. And then we also wanted the algorithm to be able to run on a microcomputer, such as a Raspberry Pi. So some of the advantages of autonomous lawnmowers include that they are safer than the traditional lawnmower in that the user doesn't have to be near the blades, which is a common cause of injury. The lawnmower was also equipped with collision, tilt, and lift sensors to stop the blade when interrupted. Additionally, they tend to be cheaper and more reliable. And since our lawnmower is electrical, that means you can reduce your carbon footprint by not using gas-powered mowers. And they are very quiet, so they reduce noise pollution. So thus the mower would overall be eco-friendly. So I hope to talk to you guys today about the YOLO version 3 program, its architecture, and show you a few outputs for each stage. And then I would also like to discuss some of the results from it, and then hopefully talk about our distance estimation solution. So the YOLO version 3 uses the DarkNet 53. It is a framework to train neural networks. It has 53 layers, hence the name DarkNet 53. These 53 layers are then further stacked with 53 more layers, which gives YOLO version 3 its 106-layer convolutional architecture. The YOLO version 3 was trained on the COCO dataset, also known as the Common Objects in Context. This dataset is actually Microsoft's large-scale dataset consisting of 328,000 images with 80 different classes. So the YOLO architecture, which YOLO standing for you only look once, the YOLO architecture is divided into 3 main components: the backbone, the neck, and the head. The backbone being the part of the network that is made up of the hidden convolutional layers that detect key features inside of the image. So these key features could mean low-level features such as multiple lines, colors, etc. The neck then processes these features with fully connected layers to make predictions on the probabilities of the class as well as bounding box coordinates. And the head is the final output layer of the network, which normalizes the entire CNN output to fit between 0 and 1. So basically a probability distribution. So some of the benefits of the YOLO architecture is that it is fast, meaning that it is able to process 30 frames per second, as well as it is able to understand generalized object representation, meaning that when given image of a real world object, so an object inside of the real world is able to recognize it, as well as when it is given an image of a piece of artwork or a drawing, it is still able to recognize the object inside of it. And so that also plays into its accuracy. So how does YOLO do this? So let's take an example. So this is an image from our autonomous lawnmower on Florida Poly grounds. This is a student walking in front of the lawnmower. So the first step that YOLO would do would be to divide the image into S by S grid cells, right? Each grid cell predicts bounding boxes and returns confidence scores that reflect how confident the model is that the box contains an object and how accurate the box is. And so each bound box has 5 elements consisting of its X and Y position, its width and height, and then the box confidence. It also consists of a class confidence, which the tensor consists of a class confidence, which is basically the box confidence as well as the class probability. So there's no object inside of the grid cell. So we can see there's only one object inside of our image. And so a lot of these grid cells will have no object inside of them. If there's no object inside of the image, and the confidence score should be 0. So this is actually what it looks like. These are all the bounding boxes that all of the various grid cells would have produced. However, if we remove all of the bounding boxes where the confidence score was 0, we will remain with only about 5 bounding boxes. To determine, so after receiving these 5 bounding boxes, I filtered out all of the bounding boxes that had a confidence score of less than 0.5, which means I was left with these 3 bounding boxes. And then to actually determine which bounding box was the correct one, YOLO performs intersection over union. I heard someone mention it earlier. It is simply like the evaluation of the overlap between the ground truth bounding box, which is actually the bounding box that was labeled inside of the data set, and compares it to the predicting bounding box. And so the bounding box out of my 3 boxes that had above 0.5 confidence score, they were compared to the true bounding box within inside of the data set to show us what the final bounding box would be. And so that was the result. And so some of my results from actually running the lawnmower on Florida Poly grounds, we collected 50 images for items commonly found at school. So people consisted of students and professors walking along the grass area, plants, which include trees and shrubs, and then animals, which include service dogs and then squirrels, and then obviously rocks that would stop the mower from running. And so when it came to people, out of the 50 images that we passed through our program, 46 were correct and 4 were incorrect. Plants, 26 were correct, 24 were incorrect, and then 40 for animals, 40 were correct, 10 were incorrect, and then rocks, 43 were correct, 7 were incorrect. And so we wanted to evaluate for the incorrect images, we wanted to evaluate what were some of the error trends. And so to give you some more information, an incorrect score was given if the program didn't recognize any objects inside of the frame, and if the program returned the wrong class, meaning that for an animal, if it returned the wrong animal, meaning a squirrel instead of a dog, then that was considered incorrect. And so for people, it almost always recognized that there was a person. It just returned the wrong object. So meaning that within the frame, if the person's shoes was the only thing showing, then it will return shoes. If the person was on their bicycle or if they had their skateboard, it might just return just a skateboard and not necessarily the person. So whenever there was something obstructing the view of the object, or if only part of the person was seen, it would name that part of the person and not necessarily a person itself. For plants, the program had trouble recognizing trees, but it did a very good job when it came to recognizing small shrubs and other plants. And then for animals, sometimes it would return a cat instead of a dog. So little discrepancies like that.
So
And then-
Gabriel, just letting you know we're at time. If you can finish within the next few seconds, it would be amazing.
Okay, great. So I used for distance estimation, we kind of took a brute force approach and we measured out and we made a list of all of the pixels that were associated with each feet inside of the image. And then after that, we used the formula, very small at the bottom, to actually calculate the approximate distance. So some of the results from that, we used all of the cases that were correct from the object recognition because we needed to use the bounding box position to actually determine to actually figure out what the distance should be. So we used the correct output from the image recognition in order to do so. And these are some of our results. An incorrect distance we're giving if the distance was more than 4 inches out of the correct distance. And then these are some of our final results where we had 86% accuracy for people, 40% accuracy for plants, that is. Animals were 72%, and then large rocks was 80%. And so I will end there and ask you guys if you have any questions.
That's brilliant. So I have a burning question, but I can't ask because maybe I'll ask in the chat and you can reply in the chat.
Okay.
But we'll have to skip the Q&A for the rest of the talk so that we can stay on track. Thank you very much, Gabriel. Super cool presentation. I love robots. Thanks.
Thank you.
All right, so let's move on. All right, thanks very much. Let's move on to the next one. So next we have a deep learning approach for deforestation prediction from, I believe, Vector and IIT. Varun is our presenter. Over to you, Varun. Varun, I think you have an audio loop back in some way.
Is it fine now?
No. No. Are you using two devices? If you are, then mute the speaker and the microphone of a secondary device. And then it should go back to fine.
Just.
All right. Okay. Are you still with us?
Yeah, hello. Is it better now?
It's much better. Okay, brilliant. Please go ahead. Just letting everybody know while it loads that the speakers will be available in the lounge after the session if you'd like to go and ask more questions personally. All right, over to you, Varun.
Yeah. So hello, everyone. We welcome you to our presentation of a paper, A Deep Learning Approach for Deforestation Prediction. I'm Varun, a fourth-year undergraduate student in the Department of Computer Science and Engineering at IIT Kanpur. This project is conducted in the collaboration of Moja Global, Vector Institute, and IIT Kanpur Consulting Group with funding from Google AI for Social Good. So these are the sections that we'll be covering in today's presentation. Moving on to the problem statement. Agriculture, forestry, and other types of land use account for 23% of global greenhouse gas emissions. Moja Global provides tools for estimating emissions of greenhouse gases. Deforestation is one of the main sources of greenhouse gas emissions from the land sector. Large amounts of carbon are stored in trees, absorbed from the atmosphere over decades, if not centuries. When the trees are cut down and used as firewood, the carbon stored in the trees is released into the atmosphere. Our goal is to predict deforestation and provide the data to governmental agencies to take suitable preventive measures in advance. How do we aim to achieve this? We plan to create an efficient machine learning algorithm to predict if a patch of land would be deforested in near future. So the steps that are involved from raw data to results, data pre-processing. The data is taken from different sources. The input data is taken from Google Earth Engine and is made up of 11 spectral bands. The target data Y of the forest cover is extracted from the Matt Hansen dataset and also involves some proprietary datasets. During our experiments, we found that working at a resolution higher than the originally provided 30 meters resulted in faster training time and more accurate models. We'll highlight this point later. Data cleaning. There are small patches of land for which the data is not available from either the Google Earth Engine or the Manhattan dataset. We use several techniques like average fill and forward fill to fix such inconsistencies in the dataset. Feature selection. The data from Google Earth Engine contains bands which may not be directly relevant to our task, such as the cloud coverage band. We have experimented with various dimensionality reduction techniques, such as PCA, to reduce the effective dimensionality of our data and faster training. We are currently using deep recurrent architectures. This is our current model, like CNN LSTM. We further plan to experiment with models like GAN LSTMs. Now coming on to model tuning, we are experimenting with different architectures and tuning. I mean, this is done, and we aim to improve and work more once we receive the feedback from forest authorities. Explainability. The final goal of our project is to empower policymakers to use AI to make informed decisions. Hence, our model predictions have to be explainable, reliable, and comprehensible to relatively less trained individuals. Going on to the workflow, you can see the broad workflow of our entire methodology. We collected data from various publicly available sources and processed them for our use case. These input features are mostly based on the Landsat imagery, and we downloaded them at yearly intervals from the Google Earth Engine. The data was arranged in a time series format with a look back of 5 years and divided into 15 charts for ease of use and faster processing. We performed normalization and dimensionality reduction operations, followed by designing and testing deep learning networks for predicting the deforestation risk of each pixel for the next few years. Some of the major challenges we faced was initially like there was absence of suitable target data set for every nation. We had the proprietary data sets for some of the nations, but a global data set was missing, in which Matt Hansen came to use, which is also publicly available on Google Earth Engine. And however, these datasets had a lot of noise at 30-meter resolution. To overcome this challenge, we started experimenting and saw at 350-meter resolution, the noise was considerably reduced, and the data size, as in the input data or size of raw data, was also reduced a lot. A lot of patches have very less deforestation, which is a good thing actually, but not for the model. We are expanding the model to Congo for getting more useful data points. Fourth is the explainability of results. For bringing a model to use in the real world, we are finding ways to explain our results and how did we get to them, to the people who are not very well informed about machine learning and its techniques. Moving on to our data pre-processing. We collected data from Landsat 7 spectral images for Uganda. The target data was taken from Matt Hansen dataset. Now we removed the null patches spread all across the data. These were presumably because of cloud cover, our missing data, but these patches were successfully removed using average filling. Resampling data to a higher resolution. The 30-meter data taken initially from Google Earth Engine was very noisy, and so we changed the resolution of the TIFFs. This led to a massive reduction in noise levels and each data point X, Y. So finally, each data point for the model can be summarized as follows. The input set of images for a patch of land has the data for 5 years. So it will be a 3D matrix of size 5 cross 32 cross 32, where 5 is the years and 32 cross 32 is the pixels. Y contains the targets for each pixel in the input image, and its shape is 32 cross 32. So we also shortlisted the coordinate. Only those patches of land were selected for training and testing which had sufficient amount of forest present during the start of the study period. This helped us cuss the waste patches as city, land, and oceans. Sharding. We split the data into 15 H5 files for faster data input and output, since geographical data can be really large in size. Applying PCA to reduce the number of effective spectral bands in the data to facilitate faster training. PCA weights were calculated via normalizing through global minimum maximum bands, and post that, the 4 component weights were applied on the shards. During our experiments, we found that 4 bands are able to explain over 93.35% of the variance in the data. These are some of the sample input images to our model. These are obtained from Google Earth Engine. The left one is from Uganda, and this has the Budongo forest region, and the right one is from Philippines, which has the Luzon rainforest region. These were the regions that contain the most forest and largest amount of deforestation. So this is the plot of cumulative explained variance versus the number of components. We can see that in 4 components, we got 93.35% variance, and hence we decided to move forward with it. This is the dataset layers, the initial dataset that we get from Google Earth Engine. So band B1 gives the surface reflectance of blue color, B2 gives it for green, and so on. Note that the normalized difference vegetation index is a combination of the B3 and B4 band, and which we expect. So this is a non-linear combination, and we expect the deep learning model to learn it itself. Moving to our model, results and inferences. So this is the final architecture which we arrived at after the literature review and experimenting with the layers. We use the CNN LSTM model as it utilizes convolutions to extract spatial features and passes them through a LSTM layer to model temporal dependencies in the data. We can see the number of parameters on the right. So on the right, we have the model summary and the model overview on the left. So this table has our results, like the final results while hyperparameter tuning. We see that in regression and with a learning rate of 0.005 and with mean squared error loss, we got the max AUC of 0.83. And the best AUC score for baseline models was 0.68, so the results are promising. We are in talks with the National Forest Authority at Uganda to explain them the results and to ask for feedback regarding future improvements. So we are also working on feature importance. We ran gradient boosting regressor, a tree-based model on a dataset to find importance of each feature for final prediction. Gradient boosting regressor trees score each feature by how frequently it is selected to split a node and the gain in accuracy such a split provides. The graph in the slide shows the feature importance of different bands of Landsat we derived. This band is closely related to the vegetation index, the 7th band here, and hence the high correlation. So our future plan of action involves experiment with more spatiotemporal models like GAN LSTMs, experimenting with transfer learning. We plan to experiment with transfer learning. Like currently we have only experimented with it on 2 patches on the same geography, but we also want to experiment it cross nation. And literature for Ethiopia suggests that using on-ground reports in conjunction with satellite images improve model performance and interpretability. We would like to extend this concept by incorporating this approach in Uganda. We also are in the process of implementing or getting explainability using saliency maps. Like using saliency maps such as guided backpropagation, guided GradCam, to obtain saliency maps to visualize the features which influence the prediction of the model the most. This would be of great assistance to policymakers as it would enable them to judge how the model is predicting a certain patch of land to be susceptible to deforestation. In conclusion, the initial results are promising. The final predictor is still in progress. With suggestions and feedback from the forest experts, we aim to build a dependable and accurate deforestation predictor. This project would soon be open sourced on GitHub on Mojo Global's repository. Thank you.
Brilliant. Thank you very much. So let's make sure, if possible, the link to the GitHub is also in the paper, if not already. And I saw some of great visuals added, so it would be great if they're also included in the paper to the extent possible in the final version. But brilliant work, super important, super relevant to the theme of the conference. So thank you very much for the presentation, Varun and team. All right, let's move on to our last. I'll have to cut through the Q&A, but please leave any messages, leave any questions in the chat or the Q&A for Varun to reply. And also he will perhaps kindly be available after this session at 2 p.m. In the lounge for any questions. Thank you, Varun, again, and team. Okay, so next. So the last talk today is attention-based remaining useful lifetime, ARRL, prediction for aeropropulsion systems. This is from Arash Nouri from Carleton University, Ottawa. Over to you, Arash.
Thank you, Asan. Just going to share my screen real quick. Screen number 1. Can everyone see my screen?
Yes.
Wonderful. All right. It's a bit laggy, but I believe it. Wonderful. All right. So my name is Arash Nouri. I'm currently a master's student in computer and electrical engineering at Carleton University in Ottawa. And today I'm going to present you this paper named Attention-Based Remaining Useful Lifetime ARRL Prediction for Aeropropulsion Systems. So today's agenda is, first I'm going to go through the brief introduction of what I'm going to do here, problem statement, then we are going to move on to the background and literature review. And then we're going to move on to methodology, results, and lastly, the conclusion of the work. So prognostic and health management. Prognostic and health management is an active research and a multi-billion dollars per se, to be exact, industry in the field of reliability and engineering. One of the key components of PHM is predicting remaining useful lifetime of the system's components. The objective of RUL is predicting of the available time before a failure occurs within the components or subcomponents using historical raw data and determining the system health index. In this way, RUL predictions have the potential to prevent critical failures. It'll reduce maintenance costs and reduce CO2 emission, and hence becomes an important measurement to achieve the ultimate goal of zero downtime performance in industrial systems and reducing the impact of climate change. So the overall talk of today concentrates on a data-driven model to estimate the remaining operable time for a jet engine. So there are some problems associated with data-driven models in RUL prediction tasks. One of them is feature selection. Extracting performance degradation features from multi-sensor data is critical technical problem for complex system as data grow in high dimensional, and which significantly impacts the prediction performance of the model. The other problem that we're facing here is run to failure data set is limited. They typically lack the corresponding time to failure labels due to the rarity of occurring failures in safety critical systems and the excessive preventive maintenance. So due to the sensitive nature of this situation of failure and the potential legal implications, manufacturer and operators, they're reluctant to share their data with researchers and make them publicly available. So, however, there are some data sets publicly available, a few of them that we can solve this issue with. One of them is the CMAPS data sets, which is widely used in prognostic studies, containing four subsets. The data sets divided into four subsets under different operation condition and failure mode, also the sensor measurements. Every sub-data set includes a training set, testing set, and a testing RUL values, which would be our labels, and consists of 21 sensor measurements. And here you can see the breakdown of these four subsets of data. So the main purpose of RUL prediction is to monitor the health status of system equipment so that the system maintenance personnel can know the current operation status of the system equipment in real time. So they would be able to implement condition-based predictive maintenance and reduce system maintenance costs while avoiding unexpected failures in the system. So with that being said, the objective of this project is estimating the remaining useful lifetime of a jet engine according to available sensor measurements of the engine components.
All right, Shilling, you got, because you're the last talk, you got around a little bit more than 3 minutes left.
Really? All right, I'll try to speed it up. So there are a few machine learning and deep learning techniques in the literature studies. I'm kind of off track right now. So linear regression, gated recurrent units, or recurrent neural networks, and long short-term memory, of course, LSTM. So I'm just going to highlight last two because they are most important ones. So the recurrent neural network retains internal memory to process sequential data. However, RNN suffers from vanishing and exploding gradient problems with long sequences. To solve that issue, LSTMs comes into the picture to handle this issue. LSTMs are a deep learning recurrent neural network model that are created to solve this problem with controlling the amount of data that they can store and work with. However, the problem with LSTMs is they are slow in training because they are sequential models. To answer these, to overcome this issue, we use transformers self-attention, which comes from the paper "Attention is All You Need," and it has been has proved that to be superior in quality for many sequence-to-sequence problems because transformer architecture relies entirely on attention mechanism to boost its speed in training by utilizing parallel computation. So the overall architecture of the vanilla transformer that we use in this paper is like this. There are a few advantages with this approach. The main advantage is with using self-attention, we have access to each step of the input data. And this helps us to, this leaves no room for information loss as far as message processing is concerned. The other important advantage with this model is that unlike RNNs and LSTMs, they are not sequential models. So it means instead of like going taking the inputs in order, it takes all the sequences at once and process it as it needs. Moving forward, we evaluate our model with root mean squared error. Since due
All right,
to
so you got only a few seconds left, less than a minute.
if you give me like 50 seconds, I believe I can finish it. So due to the sensitive nature of failures in this industry, smaller error is preferred. So that's why we use RMSE since this error rate are particularly doesn't like a large error rate, so lesser error rate is desirable, more desirable. And according to our results, we observed that higher the number of hidden units has resulted in lower RMSE, which increase our model performance. And however, increasing the attention heads, number of attention heads and transformer block have resulted in lower, like higher RMSE, which means it lowered our model performance. In the favor of time, I have to just skip this part. And in conclusion, RU prediction is an unpredictable mechanism, and it's very important to accurately estimate RUL of mechanical equipments and performing preventive maintenance, which will result in cost-effective maintenance strategy, lowering greenhouse gas emissions.
I'll have to cut off. I have to cut us.
That was wonderful. Thank you so much.
Yeah. Thanks so much, Arash. I'll end the session right here. The papers will be published in the proceedings, and the speakers will be available with you in the lounge if you want to talk to them. Thank you very much.
All right. Thank you.